Okay, so we will continue the Jacobi symbol. So, in the last class we have seen some of the properties of Jacobi's symbol. So, using that properties we have to calculate the a by n. So, where a is an any integer, a and n both are any integer. So, then it is Jacobi symbol. Okay. And so, now today in this lecture we will just talk about how we can use this to have a primality test algorithm, which is a probabilistic algorithm, and also we will see a crypto system, Goldwasser-Micali crypto system based on this Jacobi symbol. So, first let us have the primality test algorithm. So, before that let us just try to calculate some Jacobis, like suppose n is say 9975, and suppose you want to calculate this 6278 by 9975. So, that means here a is 6278 and n is 9975. So, we know that we have to convert this into this n has to be, n should be written as the product of prime. So, n is basically, if we just verify, 3 into 5 square. So, this is coming from fundamental theorem of arithmetic. Every integer is either a prime or it must written as product of prime. So, then if this is the n, then we know the definition of this Jacobi symbol. So, basically a by n is equal to, for any integer. So, basically a by 3, 5 by a by 5 square into, these are all intos, a by 7, a by 19. So, this is the definition of Jacobi symbol. So, we will use this definition to calculate this. So, this is basically, if we use this, a is basically 6278. So, 6278 by 3, then 6278 by 5 square into 6278 by 7 into 6278 by 19. Okay. So, now we have to use some properties of this Jacobi symbol. In the last lecture we have seen some properties. So, basically here for the timing we have to use these properties, that if a is congruent to b mod n, then this is p. So, we can just have p, the Legendre symbol. This is basically these are all basically Legendre symbol. So, then a by p is equal to b by p. So, basically we will try to divide this by 3, then so this is basically, so a by p is equal to a mod p by p. So, we will divide this by 3 and the remainder will be the basically 2. So, this is basically 2 by 3, and if we divide this by 5, this a, then this will give 3 as a remainder. So, 3 by 5 square into, so this also can be verified, 6 by 7 into 8 by 9. So, now if we, so 2 by 3 we know the formula. So, this if we just check whether they are quadratic residue or we can apply the properties of the Jacobi symbol, we can easily check. This is -1, this is also -1 square, this is -1, this is -1, this value is coming out to be -1. Okay. So, by this way we can calculate, one can calculate the this thing. So, this is also can be calculated by Euler's theorem. So, basically this is A by P is equal to congruent to a to the power p minus 1 by 2 mod p. Here p is prime. Okay. So, that is why it is anyway. So, one can calculate this. Okay. So, now we will use this Jacobi symbol to have a primality testing of a integer a or integer n. Okay. Now, suppose so this is basically called Solovay-Streisand primality test. That means we have to test a given integer n is prime or not. So, primality test means we need prime in the, we have seen we need prime in our crypto system like RSA and other crypto system. We need to have primes to in the key generation. So, now how to get the primes? So, that is a challenge. So, is there any algorithm in which we can give the input, say we need 512 bit prime, we just, and can it give us a prime of 512? So, is there such algorithm? No, there is no such algorithm which can take the input as the number of bits and can give us a that many bits prime number. On the other hand, what we can do? We can test we can take an integer, odd integer, because even integer cannot be a prime. We can take an odd integer n and then we can verify whether n is a prime or not. So, this we know, this is the called primality test, n is prime or not. So, this is called primality test. So, this is one of the primality test we will talk about. So, here suppose n is greater than 1, which is odd integer, is odd integer. Okay. Now, we know if n is prime, this is by Euler's criteria. We know if n is prime, then a by n, this is then became Legendre symbol, is congruent to a to the power p here is n minus 1 by 2 mod n. Okay. So, this theorem we have seen. So, this is the Legendre symbol because n is prime. If n is prime, we have seen this result. This is by Euler's criteria, and this is true for where for all n, for all a, for all integer a. Okay. Now, if n is prime, then this is true. Now, if this is true for some integer a, then we cannot say n is prime. So, on the other hand, if n is composite, on the other hand, if n is composite, then this may or may not true. Then a by n is congruent to n to the power this mod n, this result may or may not be true. Now, if it is true, but this is for only one few a, if it is true, then we can say then we called n is a pseudo prime base A. If this result is true for a given A, then we call this is true for this this n is a pseudo prime. It could be a real prime, but so far we check this is for a. So, then if a by n is congruent to a to the power p minus 1 by 2 mod n, if such a exists, and then n is called pseudo prime or Euler pseudo prime base A, and if it is true for all A, if n is pseudo prime base all integer A, then it is a real prime. Okay. So, for example, if we calculate this 10 by 91. So, our n is 91 and A is 10. So, if we just calculate this Jacobi, we can verify this is 1, okay. And if we calculate this 10 to the power 91 minus 1 by 2. So, this is basically 45. So, 45 mod 91, this also can be verified, this is minus 1. So, this result is true for A is equal to 10, although 91 is not a prime, but 91, this implies 91 is a pseudo prime base 10. Okay. If it is true for all such A, then we call it is a, then it will be a real prime, but n is a composite, although there exists some A for which this Euler criteria is satisfying, then it is called pseudo prime. Okay. So, based on this we have this primality testing algorithm, which is Solovay-Streson's algorithm, which is taking an input as an integer n, and it is telling us this is a probabilistic algorithm. So, it may correct, may not correct with some probability. So, the probability of success. So, this is taking an integer n and it is telling us whether it is a prime or not. Okay. So, what we are doing? So, we choose a randomly a integer a from z n minus 0. Choose a randomly from z n minus 0. So, a we are choosing from this is randomly from 1 to up to n minus 1, we are not taking 0 as in. Now, we calculate this symbol Jacobi. So far we should say this is a Jacobi symbol, we do not know whether n is prime or not. If n is prime, then we call this a Legendre symbol, but we do not know yet. So, we calculate this. Now, if x is 0, then surely we can say this is a composite, then return n is composite. Okay. Because then a is a factor of n. So, a divides n basically. So, then it is a composite number. So, n has a factor, that is a. Now, so this is 4, 5 is basically, now we compute that Euler's y. So, this is y is basically a to the power n minus 1 by 2 mod n. So, this can be calculated using this exponentiation. And now, if x is congruent to y mod n, then we return n to be a prime. Actually, this should be a pseudo prime based A, but anyway, since we are choosing A randomly. So, if for random choice of A give us tell us this n could be a prime. So, this is a that is why it is a probabilistic algorithm. So, then we return if this is, then we return n is a prime, which should be this pseudo prime actually. Else if this is not true, then we return n is composite, that is correct. Yeah. So, else we return n is composite number. If it is telling us it is composite, that is perfectly all right, no pseudo composite, but if it is telling it is a prime, then it is a pseudo prime. Like if we choose that 91 earlier example, if we test by this algorithm n is equal to 91, okay, and if it is happened that our random choice of A is say 10, then we have seen that these two are same, and this algorithm is returning this 91 is prime, which is not. Actually 91 is a pseudo prime base 10. So, this is a probabilistic algorithm. So, it may correct, may not correct, but if it is telling us n is composite, then it is correct. Okay. So, this is the one application of this Jacobi symbol in the context of primality test. Now, next we will talk about a crypto system based on this Jacobi symbol. Okay. So, this is a public key crypto system. This is called Goldwasser-Micali. Crypto system. This is a public key crypto system. So, let us just recall, we have two party Alice and Bob. So, now Alice want to send a message to Bob, and in public key. So, Alice need to get Bob public key. So, that means Bob needs to generate Bob's public key private key pair. This is the Bob's secret key or the private key, and this is the Bob's this is the Bob's public key, which need to be sent to Alice in order to get the message to be in order to Alice to encrypt the message and send it to Bob, and this is the secret key of Alice. So, this key because Alice has to send, Bob is the receiver. So, Bob has to run this setup phase or the key generation phase. Okay. So, in the setup phase, so Bob is choosing two prime number, let P and Q be two prime number. Okay. And then Bob is computing n, which is basically P into Q. This is the setup phase done by the receiver Bob. Bob is choosing this, and then Bob is choosing a m, which is basically such that m by p is equal to -1 is equal to m by q. So, that means m is non-quadratic residue mod p and also non-quadratic residue mod q. So, m does not belongs to does not belongs to quadratic residue of mod p, and also m does not belongs to quadratic residue of mod q. So, m is a non-quadratic residue of mod p and mod q. But then by what is then m by n? So, m by n is then basically so this is m is equal to p q. So, m by n is basically m by p into m by q small m. So, this is 1. So, by seeing this we may see that we may guess that m could be the quadratic residue mod n. So, this is the quadratic residue. So, we have to define the quadratic residue mod a composite number. So, just quickly we can define. So, so if we have a composition number n which is a product of 2 prime. So, any number is either product of 2 primes or prime factorization. Okay. So, a number a is a quadratic residue mod n if and only if it is quadratic residue in both p and q. If and only, this is the definition of quadratic residue on a composite number. If and only if a is a quadratic residue mod p and also a is a quadratic residue mod q. So, if a is a quadratic residue both these primes, then we say, because we know the definition of quadratic residue based on a prime modulo p or modulo q, then we say a is a quadratic residue mod n. But by seeing this definition, this Jacobi symbol, this could be tell us that a could be m could be a quadratic residue mod n, which is not true, but it is. So, that is why it is called pseudo quadratic residue. So, that is why m is belongs to q r of n. This is the set we can define as pseudo quadratic residue. So, it is not a quadratic residue, although we are getting the this Jacobi symbol is 1. So, this is called pseudo quadratic residue. Okay, so, this is the setup phase. So, this is the setup phase. Now, after run this setup phase, Alice, so Bob's generates this key. So, Bob's key set is basically, this is the key set n p q m such that p is equal n is equal to p q, where p q are prime, where p and q are prime and m is chosen to be such that m belongs to q r in pseudo quadratic residue. That means, m is chosen such that m by p is equal to minus, this is the legenda symbol. Legenda symbol of this value m is minus 1, legenda symbol of value under mod q is minus 1. Okay, so, this is the key generation. So, this is doing by Bob, and so this is the one key content n p q and m. Now, this p q are basically secret key of Bob, secret key, this is db of Bob, this is p comma q, and these two basically is public key of Bob, public key. So, eb of Bob is n comma m. So, eb of Bob is public. So, it is available to the sender, which is basically Alice. Now, Alice wants to send a message. Here message space is basically 0 1. So, it is a 1 bit encryption basically, this crypto system. We can encrypt either x, which is 0 1 bit, and the ciphertext space is basically Zn star, and key space we know, this is the key space. So, now what is the encryption? So, let me just erase this. So, yeah, so So, what is the encryption? So, Alice got Bob's public key. So, encryption will be like this. So, Alice choose a plain text, suppose x is a plain text from this 0 1, it is either 0 or 1. So, encryption of EB x, now Alice choose a R, randomly Alice is choosing a R. So, this R is coming from, so this is Alice is choosing R, R is randomly Alice is chosen from Zn star. Okay. So, the encryption of this along with R is basically m to the power x r square mod n. Okay. So, m is known, m is one of the public parameter of Bob, and R Alice is chosen, and r square Alice can compute m to the power x. So, if x is 0, this is 1, if x is 1, this is m. So, this is say y. So, this y is the ciphertext, y is sending to Bob. Now, how Bob will get back the message? Now, that is the decryption phase. Now, how to decrypt it? So, Bob is having his secret key, which is basically PQ. So, Bob has to check. So, if y is a quadratic residue mod n, then it is basically, then x must be 0, because this is just must be r square. So, the decryption is like this. So, decryption of dv on y is basically, so it was 0 if y is a quadratic residue mod n, it is 1 if y is quadratic non-residue. So, Bob has to check whether y is a quadratic residue mod n or y is a quadratic non-residue mod n. So, to check that, because if x is 1, then this is m. So, this cannot be the square of something. So, to check that, what Bob can do? So, Bob has to calculate this number. So, y by p, Bob can check this, whether this is p minus 1 by 2, sorry, Bob can check this mod p. So, then and also Bob has to check y by q is congruent to y to the power q minus 1 by 2 mod q. If any one of these not satisfying, then Bob can easily say y is not a quadratic residue, that means corresponding x is 1, otherwise corresponding x is, if we both the case both it is satisfied, then y it is quadratic residue mod n, then we say that then Bob will recover x as a 0. Okay. So, this is the algorithm which is based on the Jacobi symbol, which is called Goldwasser-Micali algorithm. So, this is a probabilistic algorithm. So, yeah, thank you.